Introduction to reference frames. Alright, tell me, is this stick big or small? Even though the question is simple, the answer is difficult. Let's make the question a bit simpler. Now, can you say, now the answer becomes easier. The stick is big. Alright, now can you say, is the stick small now? Here we realize that to describe the state or property of something, we need to compare it to something else. Without something to compare against, we cannot describe the state of an object. To describe the property of anything, we need something to compare it with, and that thing is called the reference frame. This is the basis of both general relativity and special relativity. What's the shortest possible path in a straight line? Because a straight line is the path of shortest distance. However, in reality, this doesn't always happen. This made Einstein think, light must always follow the shortest possible path. So, does that mean a straight line is always the shortest path? Think about the Earth. If you think about the Earth's surface, the shortest path between 2 points is not a straight line. Why? Because the Earth's surface is not flat, it's curved. On a curved surface, the shortest distance is not a straight line. At this point, Einstein began to think, what if gravity's main cause is the bending of space itself? Due to heavy objects, space bends, and because of that bending, the shortest path also bends and becomes curved. But to express this bending of space mathematically, Einstein needed a very complex geometry of curved surfaces. For this, Einstein reached out to his college friend, mathematician Marcel Grossmann. This geometry of curved surfaces is called Riemannian geometry. Normally we know that the sum of the angles inside a triangle is 180 degrees. But on curved surfaces, the sum of the triangle's angles will not be exactly 180 degrees. It will be either more than 180 degrees or less, depending on the type of curvature. With the help of his friend, Einstein solved the mathematics behind how space bends. Finally, in 1915, Einstein published his general theory of relativity. According to general relativity, there is no force acting between two objects. That is, there is no actual gravitational force. Or in other words, gravity is not a force. Instead, what happens is, due to the bending of space around an object, other objects follow curved paths. It's kind of like this illustration. This is a two-dimensional visualization. If we want to show it in 3 dimensions, the illustration would look something like this. Around a massive object, space bends inward toward the object's center. How much space bends depends on the mass of the object. In reality, this is the simplest way to understand the bending of space. Here, think of the cloth as space. Now look, the heavy object bends the cloth, just like a massive object bends space. Now, if you place an object on the cloth and push it in a straight line, it will naturally follow the curved path created by the heavier object. All objects follow these locally straight paths, but these paths are curved due to mass bending space. This is why an apple falls from a tree to the ground. Not because there's a direct pulling force, but because the apple is simply following the curved path in space-time. Imagine two people starting a journey from the equator toward the North Pole, both walking in straight lines. As time passes, they get closer and closer, even though no force is pulling them together. This happens because they are walking on a curved surface. Similarly, an object orbiting another object behaves the same way. The object is just following a locally straight path, but because of the curvature caused by the heavier object, the path itself curves. After Einstein published General Relativity, he faced a lot of criticism. This was because Einstein essentially denied Newton's concept of gravitational force. However, through general relativity, by describing the curvature of space, the motion of planets could be explained with much greater accuracy, something Newton's gravitational law could not do. Still, many scientists were reluctant to accept this new theory. Finally, 4 years after publishing General Relativity, the theory was conclusively confirmed. In the early 1920s, during a solar eclipse, astronomers photographed stars. This was the only time it was possible to conduct such an experiment because, under normal conditions, the sun's brightness makes nearby stars impossible to photograph. If Einstein's general relativity was correct, the positions of stars near the sun would appear shifted, because the light from those stars would pass close to the sun, bending due to the sun's gravity. Because of the sun's mass, the space around it bends and the light follows that bent path. This experiment successfully proved Einstein's theory. In summary, this is the core concept of general relativity, the curvature of spacetime. One important point: throughout this entire video, I kept saying space bends, but actually it's spacetime that bends. That is, along with space bending, the flow of time also changes. When we discuss time's behavior in detail, we'll call it general relativity in the